We're going to be finishing off 7.3, looking at half angle identities. And like I said, a lot of these identities have been building one after another. So double angles came from the sum formulas, and now these half angles are actually going to come from the double angle formulas. And it's going to be taking each one of these angles and solving for either sine theta in this example and cosine theta in the third version. But to do that, you would be replacing theta with alpha over 2. Now what does that do? It simplifies this double angle, but then creates this half angle in our cosine. And that's why we call it the half angle identity, because it becomes cosine alpha over 2 equal to plus or minus, let me lower that, oops, plus or minus the square root of 1 plus cosine alpha all over 2. And then we have the half angle for cosine alpha over 2 equals to plus or minus square root of 1 minus cosine theta this time. 1 minus cosine alpha over 2. And there's different versions for tangent depending what you Google or what book you're looking at. So I'm okay with either version, but the example that I'm going to show is 1 minus cosine alpha over 1 plus cosine alpha. And again, the idea is because, well, tangent is sine over cosine. That's how we get the 1 minus cosine alpha and the 1 plus cosine alpha. Now, the way that I'm going to use them, there could be more. You could do examples of verifying identities with the half angle, but I think we've done enough versions of verifying identities. I want to use this half angle to continue helping us do something new. An identity is just another example of something that was created specifically for our half angles. So the goal is to find the exact value without using a calculator. So we've been able to do cosine of 15 degrees before. Using the sum and difference, right? We did 45 minus 30, or you could do 60 minus 45, right? 15 degrees is equivalent to pi over 12. So either version of this is okay. But I'm going to show you how we can use the half angle to help us get the same value. Now, it's not going to look like the same answer from the sum and difference formulas, but the overall value, if you're plugging into a calculator, will give you the same thing. It just looks different. If you were to simplify it, you can get to the correct answer. Now, just like the sum and difference formulas, you always wanted to have the original value still in the argument. So when you do your manipulation, you shouldn't be changing the value. You should be altering it to maybe look different, but I'm not changing it I'm not changing its overall value, right? Like, for example, like 1/2, I can write as 2 over 4, 5 over 10. I'm altering the way it looks, but the overall value is still the same. And if we see our formulas, they have this angle or degree being divided by 2. So it's not that I'm going to divide my angle by 2, because that would completely change the overall value. The idea is I'm trying to rewrite it in such a way that it has the 2 in the denominator, but still overall represents 15 degrees. Now, when it comes to radians, that might be a little bit trickier, right? But the idea is I have to take that radiant and write it in such a way that's being divided by 2. Again, don't divide by 2. That will change the overall value. So the quickest way to rewrite some radiant, right, over 2 is multiplying the radiant by 2, and then you have this division by 2. Because essentially what I'm doing is I'm multiplying by 1. But I'm not going to multiply to the numerator and denominator, because that's just going to keep it the same. That's not going to allow me to see what's going on. Now, if I were to multiply 2 to pi over 12 first, that might seem like it's going to give me pi over 6 if I simplify it. And then I leave my 2 in the denominator. Because if I were to divide pi over 6 by 2, I would multiply by the reciprocal, which would then take me back to pi over 12. With the degrees, like I said, it's definitely much nicer. 4 degrees. Now again, there is a way to convert from degrees to radians. I haven't talked about it too much, but to make a quick note, this is the best time as any that if you're ever converting from, let's say, degrees to radians, well, I have to take the degree and multiply it by pi over 180. Because what this does is having the degree in the denominator will simplify the degree, and then pi is going to create the radian. Right? That's the equivalency. Now, if I was trying to go from radian to degree now, that I have to take the radian in question and multiply it by 180 degrees over pi. Because pi is simplifying the unit for radians, and then the degrees is introducing the new notation. And again, the idea is pi is equivalent to 180 degrees in terms of position. But obviously, there are two different forms of measurements. One's a length and one's an angle. But they represent the same position. So if you ever find yourself wanting to convert from degrees to radians or radians to degrees, you can just go, for example, radians to degrees, I would have to multiply by pi in the denominator and then 180 in the numerator. And then I just divide 180 by 15. Sorry, by 12. So if you were to take 180 over pi, the pi simplify, 12 goes into 80 15 times, leaving me with 15 degrees. But again, just a quick way of doing that. Now, Now that I have my double angle, I am going to then take that angle in the numerator, because if I look back at the formula, alpha's in the numerator, and that's the angle that gets used inside our formula. Now, how do I decide if this is positive or negative? Well, that happens right at the beginning of this problem, because if I draw a quick coordinate system, I know that 15 degrees, well, that's somewhere here, right, in quadrant 1. And what we know about cosine in quadrant 1 is that it's positive. So this was just a quick note. I should probably move this. It's not benefiting us at the moment. This is just for future references. Let me box it so it does not get confused with any other information. Okay. So here, and I'll have the formula. So I know it's going to be positive because angle 15 is in quadrant 1. Don't base it off of the numerator, right? This is not 30 degrees. This is 15. This is the ultimate say. This 30 is just so we can use our formula, which would be 1 plus cosine of 30 degrees divided by 2. Luckily, we know what cosine of 30 degrees is, right? We go 1, 2, 3. So we're talking about cosine. 30 degrees is at the 3's. When I say 3, that means square root of 3 over 2. So that's going to look like 1 plus square root of 3 over 2 all over 2. And if we continue, you want to get your fractions to be the same. So I will multiply by 2 to both numerator and denominator, leaving us with 2 plus square root of 3 all over 2. Again, don't get that mixed up with this original fraction divided by 2. But let's not forget, when we divide by a fraction or divide a fraction, you always have to multiply by the reciprocal. So that's going to be 2 plus square root of 3 all over 2 times 1 over 2. Now, I want to highlight this because the 2 is this 1/2 that I'm using, which will give us the square root of 2 plus square root of 3 all over 4. And then, using a quick rule of radicals, that you're allowed to rewrite a radical that has a fraction in the radicand into 2 separate radicals. And that will leave me with the square root of 2 plus square root of 3 all over the square root of 4, which we happen to know is 2. Now again, this isn't, a calculator would make this much, much easier, but it's good practice on seeing how there's the versatility of these identities and what they can do for us. Now, we were able to do 15 degrees before, right? But I want to show you a degree that we weren't able to do before. And because And because of this half angle, we're able to do this now, and that's 22.5 degrees. And the same trick, right? I rewrite this as sine of 45 degrees divided by 2. So that's still 22.5. And now, luckily, I know 22.5 is still in quadrant 1, which sign is positive. And that's going to then become positive square root of 1 minus cosine of 45 degrees, of course, over 2. That leaves us with 1 minus, and we should always remember the 4's, or 45 degrees, real quickly. And then we need to get our denominators to be the same in the numerator. And again, all this is just arithmetic. The big trick is at the beginning and then plugging into your formula. And we're doing the same as before, just a lot of small calculations. And then we have to multiply by the reciprocal, 2 minus square root of 2, all over 2 times 1/2. That then is the square root of 2 minus square root of 2 all over 4. Using this exact same rule, right, in both problems, I can split this into square root of 2 minus square root of 2 all over square root of 4. That we know leaves us with 2 minus square root of 2 all over 2. A whole lot of 2's. And that is what sine of 22.5 degrees is, using by hand. Right, so I'm ending here. Again, I could have just as easily used radians. The trick is really the same. You're essentially doubling the angle and then dividing by 2. That's what I did with the radian. I multiplied by 2, and then I divided by 2 to keep the overall value. Now we're going to move on to a new chapter, looking at polar coordinates / equations, hence my little polar bear. But I'll end it here.